standard is AES 256, so that tends to just fall off the planet there. So AES replaced both DES and triple DES as the federal standard. A 256-bit AES key would take 156 trillion years to crack all possible combinations. That is literally an astronomical number.
Now, these key sizes, they are full key sizes. They're not blocks of keys. Like in some of the other ones where you have 3 64-bit blocks for 116.
Well, again, the block size versus the key size is different. So this would be, what was the piece about the key? This key would be a 256-bit key.
Right.
And
versus the triple DES, which uses 364-bit.
No, well, it uses
356-bit keys.
Right.
This uses one 256-bit key.
Right. Which, if you think about that for a second, right? Think about all the doors, and are you going with which key, what door, right? If you go to that in the physical world, it get pretty confusing to get in your house. Well, the triple DES has that same problem. Basically, there's a lot of overhead as a result of which key am I encrypting, am I decrypting. So AES solves that problem, because instead of 3 keys and combining the encrypt-decrypt function, it just uses 1 key very efficiently. So it solves the overhead of triple DES.
And makes it more secure.
Yes, it's much faster, and a lot less processor intensive.
The triple DES multiplies key management problem.
Oh yeah, very, very bad. Then you have IDEA. IDEA algorithm. This uses a 128-bit key. The block size, as you could probably guess, is 64 bits. One popular application here is pretty good privacy, which I'll talk about later. But for right now, just know it as an email software for encrypting and decrypting. Next, you got blowfish and twofish. The key length is variable for this, so you'll see 32 to 448, but 448 is a very odd number. So that tends to be the giveaway for blowfish being the answer to your practice test questions. You see 448, it's blowfish. It also works on a block size of 64 bits. It was designed by Bruce Sneer. It was a free alternative to DES or IDEA. Source code's freely available. You can get it, and it's got a lot of applications, a lot of open source applications. So you tend to see it in like OpenBSD or Linux. Then you've got the RC algorithms. Ron Rivest is the contributor here. Still symmetric, still block ciphers. The rule of thumb is when in doubt, it's a block cipher. So it's better to say everything is a block cipher and then just learn a few exceptions, which would be, you guys want the exceptions? Mm-hmm. All right, so your exception, we probably should have did that on the slide before where we did the block and the stream, but I guess you could do it here. Everything is a block cipher except for RC4 and then 2 modes of DES. Well, 3 modes of DES. Which would be anything that ends in FB, output feedback or cipher feedback. So everything is a block cipher except for RC4, which is a stream cipher, and then output feedback or OFB, and cipher feedback, CFB. If it ends in Facebook, then it's a stream for the modes of DES. So RC4 is an exception to the block rule, and then output feedback and cipher feedback. You guys are with me? Staying on. All right. You got other additional RC algorithms. That's why I call it RCX. All of them are symmetric, except for RC4, and here's the note on RC4 being a stream cipher. Random length key. It can be used in SSL traffic on the internet. And you'll notice something about the key size of RC5. What do you notice?
Variable length.
Variable length key from 0 to 2048. But 2048, what's the highest we've talked about so far?
512.
And even that's pushing it. So now all of a sudden we're up to 2048. That's very, very large for a symmetric algorithm. Normally you see like key sizes of like 2048 or 4096 with asymmetric. So you need that size with asymmetric. But symmetrically, you normally don't need a very, think about it this way. AES, 149 trillion years for a 256-bit key. This is what, 4 or 3 times larger? You know? 4 times larger? And then you got RC6, modified version of RC5. It was proposed for a candidate for the AES. They went with something different. But this is also an RSA product. Then you have asymmetric systems. And I'm glad we did the public and private, the signing and the encrypting and verifying and decrypting. It's good. So here's your DEREX, mono DH DEREX. RSA. It's asymmetric, uses public and private key systems. It is an extremely popular algorithm that was developed by MIT, Rivest, Shamir, and Edelman when they were at MIT in '77. It's used for digital signatures. And we've gone over the encrypting, decrypting process, the signing and verifying process.
You said it was also a private key or is it a public key?
This is a public key system or a public-private key pair. In the second bullet it says public key encryption. So that means asymmetric.
Is that the same Rivest that did the RC algorithm?
What is it?
Is that the same Rivest, Ragust or whatever that did the RC algorithm?
Yeah, same character, yeah. Ron Rivest. Yeah, so as you can imagine, Ron Rivest, he's a pretty important player in the world of cryptography. He's the guy I like to think is, did a whole bunch of cool stuff in the '70s, and now he's, playing on a beach somewhere. That's what I think, anyway. He shows up to some conferences every now and then.
And breaking into everyone's systems because of the back doors he put in on all of his apps.
Oh, come on. All right. So then you got El Gamal for our Spanish-speaking friends. Asymmetric. It's a public key algorithm. It's also used in a digital. Anything asymmetric really should have some sort of equivalent digital signature eventually. El Gamal also does key exchanges. It's slower than RSA, so it's not as popular. Yo.
So, 128-bit takes trillion years or whatever. Then how come the 512-bit RSA key length was cracked?
Great question. Anybody know the answer?
Because it's because it's public-private key. This is not a secret key. And so the
Two
private
different
side is
systems.
known.
Two different ways that the confidentiality happens. And so on the symmetric size, we can get really, really strong cryptographic strength with a low key size. But asymmetrically, the math is completely different on it. So you basically have to factor prime numbers as a result. So even though you have a larger key size, basically you can factor your way out of it in a matter of time. So even though you have a larger key size,
Is that because you have the public key?
not necessarily.
The public-private, it's because of the relationship between the public and private keys. It's because of how they're generated.
Or how they're related.
Yeah.
So if we go back and just do RSA here, I like this reference because of this piece right here. Compute n equals PQ. All right? So when they are mathematically related, this means mathematically related. So they're used in a calculation. Two prime numbers, P and Q. So they're multiplied together. And so when you encrypt or decrypt, both pieces are put together to get n. But even though the key size is much longer, all I have to do is derive the prime number or factor them until the right combination of prime numbers comes out, and then I can get it. So it's almost, I don't want to say independent of the key size, but it's a different set of math altogether. So and as a matter of fact, and to get equivalent strength in asymmetric, you have to crank up the bit size.
Which is one of the reasons it is so much slower.
Exactly. And how much? Which brings up the good question of how much slower. Wouldn't you like to know?
Sure.
100 to 1,000. In some cases, I've even seen 10,000s, but I'd be willing to bet that's a little bit of a stretch. 100 to 1,000 times slower. Asymmetric is 100 to 1,000 times slower.
Well, that makes sense because you're talking, 2 to 3, orders of magnitude larger key sizes.
Okay, I got about that. So what I like about this is seeing how they're mathematically related, but you can't derive P by knowing Q. It's not like you can do, because remember, your number is equal to the combination of both of those. So it's not like you can just do math here and figure out what P is. You can't do n divided by Q is equal to P. That doesn't work like that. But you can do P times Q in terms of prime numbers, but who knows what the prime number is going to be?
Basically brute force.
Yeah, you have to try the combination of all possible prime numbers here to brute force this.
Which is different from trying all the possible combinations
Right.
of 256 bits.
Right.
You only have to choose prime numbers within that.
Right.
Right, so that simplifies it in a sense.
By a huge factor.
Well, right, because you only have to deal with prime numbers. And, we can pretty much go through all those. There's only so many possible combinations of prime numbers.
Well, when you get to large bit sizes, then when you get up to large numbers of bits, then prime numbers get difficult to calculate.
So, write these down. Your key words here for understanding this is factorization. Factorization. That's how you break into RSA security. You got to factor prime numbers. This is based off of the difficulty of factoring large prime numbers, and that's how you break into RSA's algorithm. The difficulty of factoring large prime numbers.
Well, and technically you don't factor large prime numbers because they're not factored. What you're really factoring is the modulus.
Right.
Yeah, okay, yeah. Mathematically.
Yeah.
Accurate, yes. Well, right, and now that I'm digging into my head here, it's the difficulty of factoring prime number. No. Oh, I want to see my other slide now. Difficulty of factoring prime number? Well, can we prove that with the RSA slide? The mod to the n. The ciphertext is equal to m, which is your message, and an e. I haven't done this math in so long. Then to the mod n.
Less than encryption, to decrypt, which is really going to try and break it, is computing the modulus of n.
Of the message and
Right.
encrypting versus the ciphertext and decrypting.
Right. Knowing this, a computer can be programmed to do this fairly quickly, I would think.
Well, either way, you can go through the decryption if you want. If you really want the mathematical example, that's way beyond the scope of this class. So I'm gonna.
Yeah, but that's how you would program a computer to brute force
Right.
the decryption.
Right. That's true.
Is using those equations.
Right. All right. So RSA, lot larger bit size. Then you got L-gamal or L-gamma, if you want to insult them. Asymmetrics, public key algorithm using digital signatures, also does key exchange. It's not as widely used because it's slower. I think we just did this one. And then it was used by NIST for the basic of the digital signature standard. And you have DiffieHellman. Your keyword for this one is the first asymmetric algorithm. Designed in '76 by Whitfield Diffie and Martin Hellman. You should know those names. You won't find those on the back of a cereal box, but Whitfield Diffie and Martin Hellman. That's where the DiffieHellman comes from. Technically, this does not encrypt. This is a key exchange only protocol. But if there is that the asymmetric piece used for exchanging a secret key over an insecure medium. So let's define insecure medium.
Everything.
The internet.
Anything that you don't control or doesn't have encryption would be insecure. So the internet is a great example of both.
So this is only for public key exchange, basically.
Because all it does is key exchange. Exactly.
Private key for private key exchange, right?
Right. So really the successor to this is really the IKE and the ISACAMP. That's where those were derived from. The internet key exchange and key exchange algorithm and the ISACAMP. We'll see those. Then you got elliptical curve. This is based on the elliptical curve mathematics. If you ever used a program where it said wiggle your mouse around a bunch of times to generate your encryption key.
No, I haven't.
Well, there are programs that will say, hey, move your mouse around in a bunch of circles to generate your encryption key. TrueCrypt, for example. There's a BlackBerry component too that'll do that, I think.
I don't know
For Des, for Des server. So you can encrypt your emails on your BlackBerry, I think. Anyway, all right, so this is basically, goes off the principle of no two people will ever draw the same circle. Or the same elliptic curve, or probably a better use of words. You can have smaller and faster keys that are equivalent to asymmetric standards. So an elliptical curve of 160 bits will equal that of a 1024-bit RSA key. You will see these sometimes on smart cards. Or, note these keywords here. Provide better performance on hardware limited devices. What is a hardware limited device?
Cell phone.
Smartphones. Or cell phones, smartphones. Smartphones can possibly use elliptical curve. Then you've got the hybrid. This is when you combine symmetric and asymmetric. So the actual key is used for the encryption and decryption, the symmetric key. And then you use asymmetric to protect the infrastructure so that you can transmit that key securely. So you can transmit the symmetric key securely. In some cases, you'll actually see this referenced as a digital envelope. So the envelope would be the asymmetric pieces and the letter would be the symmetric pieces. In my example, it's both. You're combining both, symmetric and asymmetric. So the envelope protects the message while it's in transit. Would you agree or disagree? And then, of course, you need to actually be able to read the message, and you would do that symmetrically. So hybrid really brings us to a public key infrastructure. We mostly use this for authentication. It's an ISO standard, and it's based off of the X.509 framework. I want you to circle that because X.509 version 3 is our standard for digital certificates. If you go to your certificates on a Windows Explorer box, you will actually see X.509 version 3. That's the framework which we use. So X.509 for you means digital certificate. Can I make your lives easy?
Yes.
Now, if I were to have a very technical conversation with you on public key infrastructure, most people would just want to get up and run.
Yep.
But it's so easy, it's not even funny. You have a driver's license?
Yep.
All right, that's your digital certificate. The Motor Vehicle Administration, that's your public key infrastructure. And you can walk through this in the real world and then translate it back to the logical world. So you're the Motor Vehicle Administration, that would be your certificate authority. And you can write down the equivalent next to each of these. Don't you have to go register for a driver's license?
Yep.
Just like you went down to the DeER's office and got your certificates? Or CAT card, rather. Your certificate, that is your driver's license. The key would actually be on, it's your public key, your private key pair. And in this case, because our driver's license don't encrypt stuff, we'll just have to roll with that on that one. The users, that would be the owner of the license. That's an easy one. Think about this one for a second. Do you believe that the Motor Vehicle Administration has a certificate repository? So what does that mean?
It's a list of all the certificates in
A
this.
list of all the people who has a driver's license.
DMV database.
DMV database. You guys call it DMV or MVA? DMV down here. Do you believe that they have a driver's license revoking system?
Yeah, called getting too many tickets.
We call it, you get too many tickets, the certificate authority needs a way to revoke your license so that if you get pulled over and they check the revoked list, they can go, oh, you're not supposed to be driving. We're going to have to ask you to step out of the car, sir.
Could keys, for an example for keys, wouldn't a picture on an ID be a public key?
Why? Because it can go anywhere?
Yeah, and it identifies you.
Yeah. But we don't have two licenses. We don't have a public license and a private license.
So really your CAT card, it's on your CAT card.
Yeah, it's better just to go
protected in the
CAT card.
Okay.
So the analogy works a little bit better for the harder stuff, but all right. So, do you believe that they have a revoking system, right, to revoke licenses? Sure. Do you believe that they have a way to back up and recover the driver's licenses that they've issued? Let's hope.
If you lose one, you can go get another one.
If you lose one, could you go get another one? If you can, then they have a backup and recovery system. Do you think that they have a history of how many driver's licenses they've issued to you?
Yes.
That's
Piece
part
of
the
cake.
database.
Now, cross-certification is really thrown in here. I normally don't talk about it here, but basically a cross-certification is a trust with another company.
Like another state.
In this case, it would be another state. So, is your driver's license good in another state? And if so, for what? Can you drive, or not? Also you could add versioning in here. You have versions of your driver's license too, just like you can have versions of digital certificates. And is your driver's license time-stamped?
It is got an
Issued
expiration
and
date.
expired. Absolutely. Or client-side software. It's somewhat transparent. Normally we just stick our CAT card in our keyboard now and call it a day. But you may need some sort of software to actually read the contents of the CAT card and say, hey, go to the certificate authority and authenticate me. So now that you look at it in terms of the Motor Vehicle Administration, that's pretty easy, isn't it? It brings it right back to reality. So you don't have to learn all the new complicated stuff, you just have to relate it to something you already know. And all of a sudden fruit falls from trees and you just walk around, put the fruit in your bucket, get as many low-hanging points as possible, and that's the strategy here.
What was the first two keys now that you use that?
This is the Department of Motor Vehicles, and this is really the same thing, but they split the function. So think about it as one office to go register for your driver's license, but then you pick it up at another office. The thing is you supply all of your, hey, I want a license information to registration authority or DeER's office, basically. And then they're going to send it over to another office to actually create the key. Then they ship it back to DeER's where you can pick it up.
Which is not that different from the DMV. You go to the DMV and
Wait in one line.
wait in one line.
So in the registration authority, you verify your identity. You
Yeah.
register and verify
Exactly.
your identity, and then they take that identity and they bind a key pair to it. That's
Exactly.
a certificate authority.
Which now brings up the subject of trust. So you have these well-known certificate authorities like VeriSign, Entrust, Equifax, GoDaddy. There's a couple of new players in the game there, and VeriSign just got bought out. So they're all very, very well known in the world of this stuff, and so we trust them. But I myself could create my own certificate authority and call it leo.com, and the problem is you're going to trust it? No, you don't know who I am. You're not going to trust my keys, you know. You're not going to use
If it
my
says
system.
legal, I will.
Yeah, well, thank you, but nobody else will. You're the only person. I'll be able to send encrypted messages to you and nobody else. All right, so you had a couple more questions on the roles, the players? Well, remember, we got to get in and out of the data, so since we're combining symmetric and asymmetric in a public key infrastructure, your keys will be your public and private key pair. Not exactly a convenient way to do that in the motor vehicle administration. So, but what the motor vehicle or DMV example does, it gets us used to the players. So it's the same exact players and concept, it's just all done on a technical level and not on a physical level. So the role of certificate authority, this is what they do. It's basically a system that stores and distributes certificates to users or services or hosts or anybody that wants to use, basically Drive. Provides a third-party verification process, which brings us up to the two types. You have public types and private types. Public types are the ones that you use out on the internet, like VeriSign, Equifax, Entrust, Komodo, or any of those other ones. And then you have private, which is basically your anything ending in .mil, which is what you have on your CAC card. And that's inside an organization. So your DoD certificates are private certificates. They only work for the DoD. Which is why you can't send messages encrypted to anybody outside of the DoD.
And the point you were
Well,
making,
you can, but they just can't read them.
the point you were making a minute ago with Leo.com being a public certificate authority is that these major players are trusted to protect all that information and have the infrastructure to ensure that the keys that they're providing are valid keys, because that's where you're going to see if it's valid.
It's all trust. It's all
Right.
trust-based.
Right.
Yeah.
That's where you go actually to VeriSign to see, is this a valid certificate?
Right. And they have a public-facing revocation list, so if anybody messes it up, they just revoke the certificate. Your registration authority.
But is that, I want to follow on, is that a weak link in all this? I mean, what can be disclosed if somebody in VeriSign has access to all this information and sells it? What is actually being sold? Are the
Why is
actual
VeriSign-
keys being sold? Both public and private keys being sold? Or just the public keys, which is silly?
No, you need the public and private key pair.
So what do
So
they
in other words,
have
what do you
that
buy
can
from
be?
VeriSign?
Yeah.
You buy a public and private key pair.
You buy the service that registers you, gives you an identity that they offer, that they say we stand behind it at some level of assurance, right? Different
Right.
levels, and it gives you a public-private key pair, and they're telling you that you're the only one who has a private key for it.
But they really have no information beyond that, and the fact that they're basically vouching for you on a loan.
Money. This all comes down to money.
Right. You're paying them to vouch for you,
Yep.
that
And
you
so
are who you say
The
you
real
are.
question is, how strong is that
Right.
identification?
And that's the
that
question.
registration that takes place.
And how secure is it?
Right. Like in some places, you can just get a certificate over the internet. You can say,
Yeah.
I'm John Doe, I'm George Bush.
some
They might
cases-
not let you say I'm George Bush or Barack Obama, but they'll let you say you're anybody else.
The certificate on my website was free, part of a HostGator piece. So I took the free certificate and said, okay, we'll roll with that. So it encrypts the logo process, and that's about all I care for, but I'm not really using it to identify me or send encrypted messages, so I don't care. It doesn't affect me in that case. I'm only using it to secure the login process.
Okay. He's looking at me, I gotta stop.
All right, fair enough. Registration authority. This is an entity that verifies and validates the request from the user. So again, you want the company like VeriSign to stand behind the user. In some cases, if you just pay them a small amount of money, they'll issue the certificate right over the internet.
So that's an administrative and a policy control over how you do that.
Exactly. But you also could pay VeriSign to basically do a background check on you, an extended validation certificate, and those get pretty lengthy and time consuming to do. I just helped a friend do one, and literally it's a background check. In some cases, if you own a business, you have to have your business listed in the business directory of your state before they'll issue that certificate. So now you're throwing a state, another factor in there. So if you're a newly created business and you need to get your business registered to the state because these companies are going to verify that you are who you say you are, now you got to throw in a state there. That could take you 6 weeks right there just to get your name on a website somewhere, publicly searchable and verifiable. So the registration authority forwards the request to the certificate authority. So write this down. Registration authorities do not create certificates. The certificate authority creates the certificates. The registration authority is just the administrative front end.
Say it again.
The registration authority is the administrative front end for the certificate authority.
So most of us have CACs. So when you go pick up your CAC, you're really talking to an RA.
Yep, DEER's office is your registration
Your
authority.
office is your registration authority, and then they go back and actually pull your keys from.
Well, when they put their card in their writer, that must be going to a certificate authority somewhere.
That's the
Goes
reason
back
why.
to the certificate authority, and it writes that card. They never see it.
That's why you have to go sit back down while the car's being wrote to, and then come back and actually get it issued.
Yeah, you're right.
Don't pay attention to the guys behind the curtains, right? This is the Wizard of Oz 101 here. Nobody can know how that stuff works.
Here's the office you go to.
Right. All right, so your certificates, all right? This is your driver's license. You need to know that it's X.509 version 3, and there's different classes that are available to do different things. So I like to think of classes kind of like functions a little bit. Like in the motor vehicle example, we have the classes of license. You have Class A license, B, C, what can you do with it? You can't just get in a big rig and drive it. You need the appropriate license. Or that license has to provide the appropriate function. So you have classes that you can use for that. You have classes of certificates, and then you have also attributes on the certificate that say, here's what I can do with it. I can sign email, I can encrypt email, I can verify.